Good morning, everyone. So, welcome back to the course of transport phenomena in mesoscopic and nanoscopic systems. This is basically our class number 6. So, last day we have been discussing about the vectorial representation of basis vectors and representation of basis states, eigenfunctions, and arbitrary wave functions and operators in matrix format, and we have discussed about Dirac, bra and ket notation, and in other words the bracket notation. Okay, so today let us first start with one simple problem, which is basically to find out the eigenstates of the position and momentum operator in space representation. So space representation basically means that a representation where the basis vectors consists of space solution of the eigenstates. Okay, so let us say that we have the momentum operator. So the momentum operator in real space representation is basically h cut by I del x. Okay, and I have to find the eigenstate of this operator to find the eigenstates of the momentum operator. Okay, so let us say eigenstates of the momentum operator are represented by P, or let us say that it is represented by Fx. Then what this momentum operator does is basically it multiplies this function by a number P. Okay. So this basically becomes equal to okay. So this is the eigenstate of our momentum operator. Now, of course, this would not be too much of a problem for a bound electron or an electron in a potential well to find this constant A, because we just need to normalize this function Fx. But here, if we do it for a free electron, in a case of a free electron, you cannot really normalize this Fx, because this electron is free. So there are no boundary condition which this electron must abide by. So this basically means that the electron wave function runs from minus infinity to plus infinity. So in this kind of situations where we have a free electron, what we generally use is the Dirac orthonormality condition. So I will repeat again that in case of the bound electron, it is not really difficult to find out this value of A. Okay, because we just have to use this condition that this inner product of F is equal to 1. But here, since this wave function is not really bounded, it extends from minus infinity to plus infinity. So this basically means that this electron is not, this inner product is not basically integrable. Okay, because it is extending from minus infinity to plus infinity, and this wave function or this eigenstate is basically extended over the entire space from minus infinity to plus infinity. So what we do here is we use the Dirac orthonormality condition. We actually replace this A by this constant 1 by 2 pi h bar. So remember that this is the case only for a free electron that we use the Dirac orthonormality condition. Okay, so if I replace this Fx by 1 by 2 pi h bar, so in this case the inner product of F with F basically becomes equal to the delta function Let us actually call this P1, because Pi would represent the momentum axis basically, P minus P1. Okay. So this is kind of, take it as an assignment problem for you. So you have to prove that if your momentum eigenstate is given by this function over here, then this condition is basically satisfied. So take it as an assignment and do it at your home. So this condition is basically known as Dirac's orthonormality condition. So when the electron is actually free, we cannot make it normalized, we cannot make the wave function normalized, but we can make the wave function such that it obeys basically Dirac orthonormality condition. Okay. So similarly, it was asked that what is the eigen function for the position operator. So let us say that we have this position operator x and it multiplies a function, let us call it f of x, and it multiplies this function by a number which is basically the position of the particle times fx. Okay. Now this y is basically a number, this one is the eigenvalue, so this one is basically a number, but this x is basically an operator. Okay, or it's like a kind of continuous variable, it's like an operator, this is not a number. Okay, now which function has this property that if it is multiplied by a continuous variable, or if this operator x acts on it, it basically returns this number y multiplied by that function itself. So it is no other than the Dirac delta function. So if x is equal to delta x minus y, then multiplying with this operator x, which is actually a kind of variable here, this is equal to y times delta x minus y, because it is only at the location x equal to y that this function has a value. At all other places this function is basically 0. So our position eigenstate is basically this function delta x minus y, and we also have this Dirac orthonormality condition obeying here. Let us consider, so for the sake of clarity, because this is delta x minus y, I would basically write this thing as f of y, f suffix yx. So that would basically help us understand this what is this value over here. Okay, so let us say that we have two eigenstates of the position operator, f of yx and f y dash x. So in this case we have this Dirac orthonormality condition again, that this is equal to delta y minus y dash. Okay, so it is, this inner product is basically 0 except in cases where this y is equal to this y dash over here. Okay, now let us go into some detail about the uncertainty principle. And the uncertainty principle, as you know, it says that a particle cannot have definite position and definite momentum of the at the same time, or you cannot measure both the position and the momentum of the electron or any quantum particle with 100% accuracy at the same time. And I have given you examples why this is bound to happen, that because the electron is a wave, you cannot really define a specific position and a specific momentum if the wave function is spread over some region in space. Okay, so when we say uncertainty, what do we mean in quantum mechanics? So So this principle is not super important from the perspective of quantum transport, but I think that since you are learning a bit of quantum mechanics here, it is important for you to know the essence of the uncertainty principle. Okay, so what is meant by the uncertainty in a measurable quantity? So in quantum mechanics, how we define the uncertainty in an operator x is basically we define the uncertainty as the standard deviation of this operator x. Okay, so how do we define is basically sigma x square equal to the operator x minus the average value of the operator x acting on this wave function psi and the inner product with itself basically. Okay, so this is what the uncertainty in the measurable value of this operator x for the wave function psi is. It is kind of the standard deviation of this measurable quantity over the wave function psi, or the average value of the standard deviation of this measurable quantity over the wave function psi. So let us consider two operators a and b. Okay, and let us define this quantity a minus the average value of a acting on the wave function psi as f. Okay, and we will also define another variable g, which is b minus the average value of this operator b acting on the wave function psi. So if you do not recognize what these braces are, so let us say that if I write x, this basically means the average value of the variable x. So here x is basically an operator. So this x enclosed within this triangular basis, this would basically mean the average value of this operator x. Okay, now sigma a square is nothing but the inner product of f with itself. Similarly, sigma b square is nothing but the inner product of g with itself. Okay, now from Shor's inequality, so this is basically an inequality which probably you have studied in complex number in your high school. So from Shor's inequality, we basically have like integral of mod of z1 x square times integral of z2 x square dx must be greater than equal to integral of z1 star x z2 x dx and square of this. Sorry, I have made a mistake over here. So this is basically, these two integrals are basically separate. Okay, and then these limits of the integral can basically be anything. So I would actually write it as x1 to x2, or let us not give any limits of integrals, because this can basically be anything. Okay, so I mean anything over which the integral is basically defined. Okay, so from this we basically have this condition that inner product of f and inner product of g must be greater than equal to g square. Okay, this is a direct result of this theorem over here. And what is this? What is this quantity? This quantity is precisely sigma a square sigma b square. Okay. Now this part, so we have this sigma a square sigma b square must be greater than equal to if g square. Okay, and we actually have the mod actually here, because there is this mod over here, so we have to write the mod sign, because this part can actually be a complex number. It is actually a number because it is inside an integral, but this can be a complex number, so we have to write this mod sign over here. Mod of inner product of f and g square. Now this is greater than equal to imaginary part of fg square. Okay, because any complex number, the mod of any complex number is basically equal to the real square of the real part, which is real z1 square plus imaginary z1 square. So this is basically greater than equal to imaginary z1 square. Okay, so mod of z1 square should be greater than equal to imaginary z1 square. Okay, so similarly, since this is a complex number, mod of this number square, or sorry, the square of the mod of this number is basically greater than equal to the imaginary part of this number square. Okay, so let me rub it here. Okay, so now the imaginary part of this number is basically equal to, so we have to divide it by I, we have to divide it by 2i actually, because when we subtract a number from its complex conjugate, we basically get a factor of 2. So fg minus the complex conjugate of fg. Okay, so this part is equal to twice the imaginary part of the inner product of f and g. So we have to divide it by 2, and because the imaginary part contains the coefficient I, we divide it by I over here. Okay, now this part is basically equal to the inner product of g and f, so we get 1 by 2i f inner product of f and g minus the inner product of g and f. Okay, so we have this relation over here that sigma a square sigma b square is greater than equal to 1 by 2i the inner product of f and g minus the inner product of g and f. Okay, now we also have a theorem. If a and b are Hermitian operator, then for any function psi we have let us say psi inner product with a psi is equal to a psi and inner product of a psi and psi, or in a much broader sense, if these are psi 1 and psi 2, then we have the inner product of psi 1 and a psi 2 is equal to a psi 1 and psi 2 over here. So inner product of a psi 1 and psi 2. Okay, so we precisely use this kind of relation here, not here, but we precisely use this kind of relation in the inner product of f and g. So this is equal to a minus the average value of a. So these are operators, so a minus the average value of a operator acting on psi, and we have this bra notation over here and ket notation over here. So b minus the average value of b acting on this wave function psi, and this must be equal to psi a minus the average value of a, b minus the average value of b, acting on this wave function psi. Okay, so the inner product of psi multiplied by these two operators acting on psi. Okay, okay, so we just break this operation over here. So psi, then we multiply these two operator combination. So there should be a first bracket over here. So we have this operator AB, then we have minus the average value of A times B minus the average value of operator B times A minus the average value, plus the average value of the A operator and B operator, and not multiplying but operating on this wave function psi. Okay, so this basically becomes equal to the psi and then this operator A B acting on psi minus this average value of A is a number, so it gets out of the inner product, and then psi B psi minus, again this average value of B is a number, so it again gets out of the inner product, so B psi B psi minus the average value of A, average value of B, and then the inner product of psi with itself. Okay, so this first term is basically the average value of the operator AB. So this basically becomes the average value of the operator AB minus the average value of A multiplied by the average value of B. So this is the average value of the operator B over here minus the average value of the operator B multiplied by the average value of the operator A, plus again the average value of A multiplying the average value of this operator B. So this total thing basically becomes the average value of this operator AB minus the average value of A times the average value of the operator B. Okay, so similarly if we actually do the inner product of G with F, this basically becomes equal to the average value of this operator BA minus the average value of this operator B, the average value of this operator A, which is equal to average value of BA minus the average value of this operator A times the average value of this operator B. Now, so this average value of this operator B A is not equal to this average value of this operator A and B. Okay, because the operator B A is not equal to this average this operator AB if the commutator of A and B is not equal to 0. This we have already seen for the position and the momentum operator, that the commutator, their commutator is not 0, and so this two operator acting subsequently may not be the same if we reverse their order or if we change their position. Okay, now so we finally arrive at a point where this sigma A square sigma B square is basically greater than equal to 1 by 2i inner product of Fg minus inner product of G and F, and this is basically equal to 1 by 2i AB average minus BA average. Okay, now this is equal to 1 by 2i times commutator of A B. Now if the commutator of AB is 0, that is if this part is basically 0, then this sigma A square sigma B square is equal to 0. Okay, so if the commutator of A and B is equal to 0, then the product of the uncertainties of this operator A and the uncertainty of the operator B is basically 0. And what I have said earlier is that if the commutator of two operator is 0, then basically it means that they share the same set of eigenstates, or at least the eigenset of one operator is a subset of the eigenstate of the other operator. Okay, so in these cases there is this uncertainty, the product of the uncertainty of the operator A and the uncertainty of the operator B is basically 0, because we can determine the eigenvalues of the wave function at the same time for both these operators. Okay, but suppose we have this operator x and p, the position and momentum, where the commutator is basically not 0. So we have already seen that for x and p, this commutator is basically equal to I h bar. Okay, if this is the case, then this product of the uncertainty of the position operator, which we write as sigma x square sigma p square, this is equal to 1 by 2i commutator of x and p operators, and this is equal to 1 by 2i times I h bar, so h bar by 2. So this is the famous theorem that the product of the uncertainty in position and momentum is equal to h cut by 2 or h by 4 pi. So this is the thing that you had actually learned in your high school, that the product of the uncertainty in position and momentum is equal to h by 4 pi or h cut by 2. So this is how you basically define the uncertainty in quantum mechanics. It is basically kind of the standard deviation of the operator. Okay, so that's the essence of the uncertainty principle, that if you cannot determine the values of two operators at the same time, or if two operators are not commuting, which basically means that the two operators do not share the same set of eigenstate, in that case you cannot really measure the value of the two operators at the same time, and that is what the uncertainty principle basically states. Okay, and I repeat again that the uncertainty as defined in quantum mechanics is kind of the standard deviation of the operator. Okay, this should be greater than equal to here and not equal to, so this is greater than equal to here. Okay, so we basically arrive at this point that sigma x square sigma y square is greater than equal to h cut by 2. Okay, I again repeat that this is not very important in quantum transport, but since you are studying quantum mechanics, you should at least get an essence of what the uncertainty principle is all about, and this is actually very important. So next we will basically study spin. Because we have already studied the uncertainty principle, I will show you that in case of spin you cannot really determine the three components of the spin at the same time. Three components basically mean the x, y and z components. Okay, now the question which you might automatically ask is that what is spin and why it is important in quantum transport. And to answer your question, remember that there is a new generation of devices that have been upcoming that relies on spin of the electron. Okay, so these are known as spin based electronics, or in collective language it is termed as spintronics, and these devices are supposed to be the future generation of devices, and a lot of research is basically going on this field to basically commercialize such devices, and we already have some of the devices that rely on spin in the market, and one such example is basically our hard drive in the computer. So a hard drive basically operates on the basis of magnetic sensing, so it is relying on spin of an electron. Okay, and a more sophisticated example would be spin based RAMs, which global foundries are trying to commercialize in the next 3 or 4 years. Okay, and why are people moving from electronics into spintronics is because spin based electronics are supposed to be more reliable and more low powered devices, and you can really scale these devices to a much smaller dimensions. Okay, so that is why, because today we want to pack more number of devices in a single chip, people are really trying to actually realize spin based devices. People have already realized, but commercialization is a different thing. When you commercialize a device, or when you commercialize a chip, you need to take many things into account and you need to think of many aspects. So that is why it's taking some time, but it has been manufactured or fabricated to a quality that can be commercialized basically. Okay, so there is enough room or enough potential for commercialization. Okay, okay, so now what is the spin of an electron? So spin is basically an inherent property. So this is an inherent angular momentum that is attached to an electron. So it is basically an inherent property of an electron. You cannot really remove this angular momentum. Okay, you cannot make the spin of an electron zero. It is not possible. And the second thing, so it is inherent. So the point number one is that inherent. So it can't be removed. And the second point is that you can basically change the direction of the angular momentum, but you cannot change the magnitude of the angular momentum. So we can change the direction, but we can't change the magnitude. So from this you can already understand that spin is a very fundamental property of an electron, and it is attached to an electron. You cannot change it. You can change the direction, you can change the orientation, but you cannot change the magnitude of the spin. Okay, it is an inherent property of the electron. Okay, and people often explain that an electron is moving like so let me draw a picture over here. People often explain that this is the axis, this is some nucleus of an atom which contains the proton and the neutrons, and then an electron is rotating like this, a point particle. This is an electron which is rotating in this direction, and that gives that gives or that causes the spin angular momentum of an electron. But this picture is actually not true, because electron is not a classical particle. So it is not that this point charge is moving around this nucleus, but if you would like to think in this way, it is more appropriate to think of it like a cloud of charge. Okay, the electronic charge is basically dispersed in space like a cloud, so it is everywhere basically in within a sphere, and this dispersed cloud of charge is basically moving around the nucleus of the atom. Although that picture is also not totally correct, but anyway, you can think of it in that fashion if you want, but it is not like a point particle is basically moving around the nucleus. Now how do you define thus the angular momentum? Okay, so the angular momentum, let us call the angular momentum operator in quantum mechanics as L, and L is nothing but it is the cross product of the position operator and the momentum operator. Okay, now Uh, so if I do the cross product, so let us see what do I get. So we are doing this in 3 dimensions. So we have 3 components of our momentum operator P and 3 components of the position operator R. Okay, so we get I times RYPZ minus RZPY plus J times RZPX minus RXPZ plus K. So these are all unit vectors. K times RXPY minus RYPX. Now one thing to note here is that, so we have already stated that x p in one dimension, so this is actually px because we were considering one dimension at that time. So the commutator of x and the momentum operator in the x direction is basically IH bar. So let me go to a different page actually. So let us actually go back to what we were discussing. So the x operator and p operator, the commutator is equal to IH bar. Okay. So we are discussing about one dimension at that time. So in 3 dimension, this commutation relation basically becomes, let us call, if Ri is the position operator in the ith direction and Pj is the momentum operator in the jth direction, then this commutator is equal to IH bar delta Ij, where delta Ij is equal to 1 if I equal to j. So delta Ij is equal to 1 if I equal to j. And this is equal to 0 if I is not equal to j. Okay, so which is another way of stating that this Rx Px is not equal to Px Rx. However, Rx Py is equal to Py Rx. And to give you a simple example, so this basically means that you can measure the position of the particle in the x direction and the momentum of the particle in the y direction at the same time. Okay, I again repeat that if two operators do not commute, this basically means that you cannot simultaneously measure the value of those two operators. But if two operators commute, this basically means that the values of those two operators can be determined at the same time. Okay, now, so what this means is that we can determine the position of an electron in the x direction and the momentum of the electron in the y direction at the same time. Okay, so to give you an example, let us consider this wave function beta xy, let us say, equals to a delta x e to the power minus I e to the power minus I py p suffix y divided by h bar. Now I can determine the position of this particle in the x direction because delta x basically means that along the x axis it is localized at x equal to 0. So this wave function, if I measure along the x-axis, or if I measure the x coordinate of this electron, it means this delta x basically means that the wave function is basically localized at x equal to 0. Now I also want to measure the momentum along the y direction. So if I want to measure the momentum along the y direction, I would operate this wave function with this operator, I minus I h bar d dy beta xy. This becomes equal to py a delta x e to the power minus I p suffix y by h bar. Okay, so this is equal to py times beta xy. So we get py as the momentum. Okay, so for this wave function we can therefore simultaneously determine the x coordinate or the x position of the electron and the momentum of the electron along the y direction. So this is just a simple way of making you understand that if we are measuring the position and momentum of the electron in separate directions which are mutually perpendicular to each other, then we can definitely do that. Okay, we can measure the position of the electron in x direction and simultaneously also measure the momentum of the electron in the y direction, but we cannot simultaneously measure both position and momentum of the electron in the x direction. Okay, so the position and the momentum operators in mutually perpendicular direction definitely commute. Okay, so let us go back to what we were doing. So we have this expression for our momentum operator, and note that this is the ith component of the angular momentum. So this part is definitely the x component. So we have ry pz minus rz py. Ly is equal to rz px minus rx pz, and Lz is basically equal to Rx Py minus Ry Px. Okay, so we have these three relations, and let us check whether we can measure the angular momentum along different axes at the same time. Okay, so let us go to that part. So we have these three relations, and to understand that whether we can measure both the x and y components of the angular momentum at the same time, we would basically take the commutator of Lx and Ly operators, and if this commutator is, if it is equal to 0, this would basically mean that I can measure the angular momentum along the x direction and along the y direction at the same time. Okay, so let us actually do this. So we have this Lx is equal to Rypz. Let me write in the line below. So Rypz minus Rzpy, and commutator with Ly is basically Rzpx minus Rxpz. Okay, so this is the commutator of Lx and Ly, and this part is basically equal to the commutator. So you can multiply these parts to get the smaller commutator. So this multiplied by this one. So this is basically equal to let me write it here, Rypz Rzpx. These are operators. Commutator of this multiplied by this with this one, which is minus Rzpy Rzpx minus this one with this one, which is ry pz rx pz plus this one with this one, which is rz py rx pz. Okay, so I'll just rub these things here. Okay, now note that which part in these equations do not really commute. Okay, so first let us go to the first term. Note that this ry basically commutes with pz, and this px also commutes with rz. What does not commute in this equation is basically this pz and rz over here, because they are measured along the same coordinate. So what we do is we take out this px and ry from this commutator. Okay, so this basically becomes equal to ry px commutator of pz rz. Okay, now let us go to this second term over here. Now again, what does not commute in this equation is basically in this equation kind of everything commutes, because this rz commutes with py, rz commutes with px, and then this px also commutes with py, and this rz also commutes with rz over here. This rz commutes with py, and this rz commutes with px. So this is basically equal to 0. Okay, now let us go to this third term over here. Now here again, by the same logic, this ry commutes with pz, rx commutes with pz, and this pz commutes with rx and pz, and this ry also commutes with rx and pz. So this again goes to 0. And now this fourth term over here, so here again we have this py commutes with rx and pz, so we can basically take it out. So we can take it out, py, and then this rx also commutes with rz and py, so we can basically again take it out. So this is rx. So what does not commute in this equation is basically this pz over here and rz over here. So this is basically becomes commutator of rz pz. So if you are having confusions in what I am stating, you can actually go in the longer path, and you can actually write these expressions for these commutators, and you can actually check it out. I have been doing this for a long time, so it's kind of easier for me to actually understand. Okay, but if you are not understanding the logic, you can basically write the complete expressions for these commutators, and you can basically check if what I am stating is right. Okay, so this ry px, we have a negative sign over here, and we switch this two operators and we multiply it with a negative sign. So this is r z px pz plus rx py rz pz. So these two are equal to I times h cut. So this becomes equal to I times h cut minus ry px plus rx py. So what is this quantity or this operator? This operator is nothing but the operator for the angular momentum along the z direction, this part. So this is equal to I h bar Lz. Okay, so we have come to a relation which is again quite fundamental, which is Lx Ly is equal to IH bar LZ. Okay. So similarly, we can derive other relations like Ly Lz. The commutator of Ly Lz is equal to IH bar Lx, and the commutator of Lz Lx is equal to IH bar Ly. So we have these three commutation relation, and what this tells me is that we cannot really measure the angular momentum of the electron in the x and y direction at the same time. Okay, so this relation basically tells me that I cannot really measure the angular momentum of the electron in x and y direction at the same time because their commutator is not zero. This relation tells me that I cannot really measure the angular momentum of the electron in the y and z direction at the same time because again their commutator is not zero. And this relation tells me that I cannot really measure the z component of angular momentum and the x component of angular momentum at the same time because again their commutator is non-zero. Okay. Okay, so let us do it up to here today. Thank you everyone.